Okay, YouTube, this is our last video in our introductory module on assessing limits, but what we're going to look at here are specifically graphs that have holes in them. And so what I want to do as a matter of this exercise is sketch graphs of each of these functions that we see here, but then also find the limits of each function as x approaches 1 and x approaches 2. And so let's go ahead and start with our f of x here. If we were going to sketch this graph, for instance, what we would get is some graph that is linear. And so we have this graph that has a y-intercept of 1 and a slope of 1, so we'll go up 1, right 1. But what we get is this graph right here. And so I suppose that if we were to sketch the rest of this in, I'll put another point on here, up 1 over another 1 here, we could see that if we were to take, say, the limit of this function of x here, as x is getting really close to 1, as we've been asked to do up here, what we're going to see is as x gets really close to 1 here, our y values, it seems, let me try this again here. Our y values, it seems, are getting really close to a height of, looks like, 2. So we can see that we get close to a height of 2 here. As a matter of fact, if we were to do the limit then of f of x as x gets really close to 2, we can see that as x is getting really close to 2, our y values here are getting really close to a height of 3. So we get a couple of limits here. Now what's going to be different about these two is when we sketch them, a little bit different. I suppose I want to simplify this first. And so I notice at the top here is a difference of squares. This is x plus 1, x minus 1 when it's factored. And as a matter of fact, this is over x minus 1. And so what we get is our x minus 1s that cancel out, and we get a simplified form of this function. Now, one thing that I do want to mention here is this, and we're going to make sure that we do mention it. We say x cannot equal a positive 1 here. And the reason why is because if x, the moment it equals a positive 1, what we get is something that gives us 0 over 0 when we plug that in, or is undefined. So by setting the denominator equal to 0, we can clearly see the x values for which our function is undefined, here in this case 1. So what we're going to do, okay, is we're going to graph this function again here, except for this time when we graph it, let's see, we go down, or sorry, up 1, has a y-intercept of 1 right here, and a slope of 1. So we'll go up 1, right 1, up 1, right 1, in order to get the rest of our graph. We say when x equals 1 here, what we'll do is we'll just put an open dot. And when x equals 2 here, in this case, we'd be fine. As a matter of fact, we'd get this right here. What we get is this graph right here. And so what we're going to recognize is that we have what we call a discontinuity. And a discontinuity is really just a hole in the graph where our graph cannot exist because it's undefined, but everywhere else it says that it behaves the same way as it does with this function. Excuse me. So we can see here that as we take the limit of f of x, sorry, g of x in this case, as x gets really close to 1, the interesting thing is that our function still, even though it doesn't exist there, okay, it's still, as x gets close to 1, is getting really close to a y value of 2. So interestingly enough, a graph with a hole in it, as we've seen in the past, can still have a limit so long as our y values are getting really close to a specific y value from either side of the x value for which we're evaluating the limit. Now, if we take the limit of g of x here, and we say, well, what's the limit of this as x gets really close to 2? Because it behaves the same way as our first function, it's also getting close to a height of 3 right here as x is getting close to a height, or sorry, a value of 2. So now for our last function, c, again, what I want to do is I want to start by simplifying this expression. Now I notice that the top here has 4 terms in it, so to factor this, we might try a grouping method here. So we say plus, and we got to keep this negative here, this negative right there. It was in front of our x with our x. But if we were to factor this by grouping, let's factor out an x squared first. We get left with an x minus 2. Over here, we're going to have to take out a negative 1. We get left with an x minus 2. It'd be clearer to see that these both have in common an x minus 2, and we're left with an x squared minus 1, excuse me, which can be also factored down even further as it is a difference of squares. So, excuse me. So taking a look at this, we can see that the top here is factorable, and it factors into x minus 2, x plus 1, x minus 1. And if we factor the bottom here, it looks like, you know, 2 factors of a positive 2 that add up to be a negative 3 would be x minus 2 and x minus 1. So interestingly enough here, we get some common factors that cancel out again, these two right here, and we get left with x plus 1. But one thing that I want to make sure we mention right here is that x is not allowed to equal a positive 2, and it's also not allowed to equal a positive 1. As a matter of fact, we're going to have holes at these x values. So our graph, the interesting thing is when you graph it as it is this line, okay, as you would this line, that is to say. So we'll go up 1, draw a dot. But as I go up 1, right 1 here, when x equals 1, it's undefined. And when x equals 2, I go up 1, another right 1 here, it's also undefined. We get this graph that looks like this right here, where we've got 2 holes in the graph. Now the interesting thing about it is if we go and find the limit of h of x then, as x gets really close to 1, we'd say, would it still exist even though our graph doesn't exist here? And because our graph, as x gets really close to 2 from either side, look what's happening to your y values. They're getting really, really, really close to a height of, you guessed it, 2. So the limit with this graph, even though there's a hole here, still exists as 2 as x approaches 1. And also the limit of this graph here approaches 3 as x approaches 2, even though it doesn't exist there. So we're going to see that when we can take a couple of graphs here and simplify them, and they all simplify down into one another, they will behave everywhere the same as this original linear function, except for they may have a hole at any of these undefined spots, which means that the limits still behave the same way on this function right here as it does on the original function, even though it doesn't exist then. Cheers.